Good day, dear participants. Thank you for joining us. My name is Evgeny. I'm a solution consultant at OntargIT. I am happy to talk on production processes modernization with IoT plus intelligence from Microsoft. So let's start our journey. Today, during approximately an hour, we are going to look at the key steps in digital transformation of production processes. We'll give you a quick overview of Microsoft Industrial IoT strategy and solutions. And finally, we prepared a small live demo on ERP and IoT integration. Surely everyone has in mind ideas and business cases for the modernization of production processes using IoT technologies. And in my opinion, one of the most inspiring examples is the business case of predictive maintenance. When the production process is automated enough that the flow of telemetry from production equipment is processed using machine learning methods and based on obtained insights, we automatically predict possible equipment failures or downtimes or critical process deviations. And based on the predicting events, equipment modes are automatically adjusted to prevent its failures. But people realize that such a digital transformation is quite complex and often requires a good partner like Microsoft. And you may have already seen the diagram on the slide. This diagram was borrowed from Henning Kagermann, who was a godfather of various industrial platforms in Germany. He created this 7-step digital transformation process. So let's start with the fact that on the first step, we need to be able to automatically retrieve data from our equipment. Then we'll need advanced integration capabilities such as edge gateways, as we don't want to connect the equipment directly to the cloud. And after that, we can already start collecting data and creating our first dashboards. And after we have telemetry and we collect it for some time, we can analyze this telemetry and identify anomalies or patterns. And then to launch telemetry data stream normalization, the data is transmitted from edge devices to the cloud and is formatted well and satisfy the common semantic model. And after we get a normalized semantic data model, we can start usage of machine learning algorithms or stream analytics to find anomalies in our data that indicate possible equipment failures. Then finally, we have insights from machine learning. We can ask a person to decide what to do, or even better, we can build an automatic system that will make a decision so it turns out to be something like a predictive maintenance system. Very often equipment connection is the most difficult stage because most other components of the system can be hosted in the cloud. And obviously, there are various tools for these components that simplify their deployment and monitoring. A large number of companies, especially manufacturing companies, have already built large ecosystems over the years. And these ecosystems consist of different components and proprietary technologies, and they are forced to continue the support of these systems. As soon as you start using equipment from a specific vendor, the chances increase that the equipment will not be compatible with solutions from other vendors. And it's very difficult to choose the right equipment because there is always a risk of making the system less flexible. If you're forced to use a software development kit with closed source code, any proprietary communication interface or protocol, specific data models by vendor, or even if you are not able to use your own local data center, these all are examples of vendor lock-in problem. That's why Microsoft decided to establish a specific set of business principles and technology principles that an industrial IoT solution built on Azure must comply in order to minimize the negative impact of the vendor lock-in problem. Some time ago, Microsoft realized that the obvious thing is that we need to use an open platform such as Azure and platform as a service components. We create an abstraction layer using open and well-established industry standards so that people can use the standards to interact with the Azure platform. In addition, we create an ecosystem of equipment connectivity solution providers, gateway vendors, so that the consumers will have a choice from multiple certified equipment. And of course, it also requires a partnership with vendors such as Siemens, Rockwell, Schneider, Mitsubishi, and so on. This idea makes the task of building complex system much easier, especially when you have equipment from multiple vendors connected with different gateway types. In addition to business principles, we also have a set of technology principles. The first is that the open source is widely used. Many things for industrial IoT solutions are open and hosted on GitHub, but this doesn't mean that source code is published and that's all. Microsoft is responsible for its quality. These are the same products as any other Microsoft products, but open source only. New features are released, ideas are accepted from the community, and of course, bugs are fixed. The open data model principle is widely used as well, because when you are modeling equipment that is 20 years old, there is a chance that the data model built into equipment is not open. But obviously, you can convert it to an open data model to manipulate data retrieved from equipment using a single approach for all the equipment from your production site. So on the next slide, you see a diagram where the industrial IoT strategy is depicted. The key components of the strategy are the wide usage of open source products, Azure as an open platform, open and widely used industrial standards, and open data model, of course. One of the fundamental components that Azure Industrial IoT consists of is the industrial standard named OPC UA. This standard is developed and maintained by the OPC Foundation. Microsoft is a member of the OPC Foundation since 1996, and starting from 2016, OPC UA is supported by Azure. Here on the screen, you can see key features of the standard. The main reason for the standard to be used is the necessity of integration of different types of equipment, establishing of a uniform data model and security principles, of course. So the OPCUA is a modern standard that describes the data transmission in the industrial networks. It's independent of hardware and platforms, and that allows to organize the data exchange between devices within different operating systems. On the next slide is depicted a typical predictive maintenance system architecture. Predictive maintenance means the elimination of failures using advanced analytics and machine learning. And this doesn't mean elimination the consequences of failure after its detection, but really avoiding failures through constant monitoring of equipment and the production environment, as well as respond on time to increase of the probability of a failure. And please note that the architecture is split into two parts. The part in the cloud starts with the IoT hub, but in the real life environment, there are a lot of places that don't have a high-speed internet connection. For example, a security policy may prohibit connecting to equipment directly from the internet. And in this case, an edge environment is organized, and inside this environment, equipment is interconnected, and some IoT capabilities are transferred from the cloud to the edge environment. Since within the edge environment there is no possibility to use cloud services of machine learning, for example, these services are hosted on edge devices within the edge environment. The edge environment in turn interacts with cloud services using the IoT hub, and the key purpose of the IoT hub is to provide two-way secure interaction of IoT applications, services, and equipment and devices. And one of the greatest things is that Microsoft develops interaction of Azure IoT services and business applications. And a good example of this integration is the close integration of the Azure IoT Hub and the ERP system from Microsoft called Dynamics 365 Supply Chain Management. Using a special add-in module to the deployed ERP system, we can support several business scenarios. And the first scenario is called production delays. And in this scenario, using telemetry data from the production equipment, we can compare planned and actual durations of production jobs. In Dynamics 365, we can set up a tolerance, and when the production job is delayed, the system automatically notifies responsible employees. Thus, it's possible to provide a timely reaction of production managers to production jobs delays. The scenario number 2 is called equipment downtime. If on the shop floor we have equipment that periodically sends idle messages to the IoT hub, then after setting up this scenario, Dynamics 365 will automatically notify the responsible employee that equipment is idle, where a particular production job is executed, and it's necessary to send a service engineer to this equipment. The scenario number three is called product quality. So let's assume that for production of semi-finished or finished products, it's necessary to comply with certain technological modes or conditions. And very often you need your production process to comply a particular temperature or humidity. If on the shop floor we have temperature or humidity sensors that are connected to the IoT hub, then after setting up the scenario in Dynamics 365, the system will automatically notify on production process deviation. For example, the temperature is above or below the specified level. And when you set up the connection between IoT hub and Dynamics 365 for these scenarios, you don't need to write any code. The telemetry messages are transmitted as JSON text, and in Dynamics 365 we simply set up the rules according to which a particular message relates to a particular scenario, production order, production job, and resource. And finally, we continue with a small demo on IoT Hub and Dynamics 365 integration with product quality scenario. So let's imagine that we have a manufacturing company that produces liquid products from dry semi-finished products. And on the shop floor, we have a big mixer where liquid product is mixing. So mixing operation is quite long and can be done only at a certain temperature. When the temperature is lower or higher than needed, product can be spoiled. Thus, the mixer is connected to a temperature sensor, so we can monitor mixing temperature to ensure that mixing is not out of the temperature acceptable limits. So temperature sensors can be connected to a network and has a digital interface, and we can connect and retrieve data from the sensor automatically. According to this business scenario, we have emulated a temperature sensor that sends messages to a deployed IoT Hub instance, and we also set up a product quality scenario in Dynamics 365. So let's move to ERP system. Well, first of all, let's look on a finished product record. In a released product form on the inventory management, in the manage inventory tab, we have a field of base attribute that is already filled with product quality value. It's a reference to a batch attribute that is called product quality. So in a batch attribute form, please look at minimum and maximum fields. In our case, we have maximum and minimum temperature values set up when mixing operation is executed. So minimum temperature is 80 degrees and maximum temperature is 101 degrees. So this is quite simple setup to tell the system what to control. We simply choose the batch attribute that contains minimum and maximum value set up in product. So the next is product quality scenario setup. Let me move to this form. This is called scenario management. And on this form, we can see scenarios available. And when I click the setup button in the product quality scenario, the first two steps let me set up how data will be retrieved by Dynamics 365 from messages that are sent to IoT Hub by our virtual temperature sensor. And on this form, we need to set up the connection between message, data, and the production orders in the system. If the ID field of the telemetry data contains value of temperature sensor, then the system will automatically link the temperature value with the production jobs on the resource that is named mixer here on the screen, and the products that contains batch attribute prod quality. It's here on the screen as well. So there is quite simple setup as well. And the final step for this demo is the notification stream that is automatically created in the system. So this notification stream is automatically created in the system based on telemetry messages from IoT Hub. You can see that in this, you can see the message list, and the first message is the notification that production job on mixer resource is out of ranges. On the right side, we can see a message, and on the right side, we can see when the process deviation occurred, and what was the real value of the temperature. In our case, it is 79 degrees. That is obviously not in this range. On the bottom, there is a list of operations for the resources, and we can prioritize operations based on the current situation. We can also resolve and dismiss notifications, and resolved notifications are saved to closed notifications. There is the closed notification list. So in this scenario, having temperature sensor connected to the ERP system, the production manager It can react on process deviations and create related nonconformance as needed. So that's it. Thank you for joining us. See you on our next events.